Let's take a look at Leet code question 53, the maximum subarray. And this also is known as Kadane's algorithm. And we're going to look at it in the context of a greedy algorithm to introduce the notion of what a greedy algorithm is. Given an integer array nums, find the subarray with the largest sum and return its sum. So a subarray is a contiguous non-empty sequence of elements within an array, which just means that the numbers need to be back to back within an array. So we have this example here. We have the numbers from -2 all the way up to 4. And if we look at this particular part of the array that are back-to-back elements, and you add 4, -1, 2, and 1 together, that's going to give the sum as 6. And that's going to be the largest subarray within the array. Because if you looked at, say, 1 minus 3, 4, for example, that wouldn't be as large as 6. And then we have these two other examples, one with just one element in the array, and obviously that's going to be the largest array element. And then also we have this one here where all of the elements together equal the total maximum array. So if you have mostly positive numbers, you will just continue to block them together, but you could have negative numbers, which would reduce from the overall sum. So let's think about how we could solve such a problem. So the intuitive approach would be for each number, looping through the remaining numbers and then adding together. So you could go -2, add that, and then you could think about -2 and 1. So all of the subarrays for each number, and then -2, -3, and so on. And then you do the same thing for 1, and 1 minus 3, 1, 4. But as you can see, that's going to sort of blow up the time complexity. Just doing that in itself would be O of n squared, and then you got to check the numbers as well. And there's actually a way to do this in O of n time and this is why it's known as Kadane's algorithm, because it's just like a, it's a very well-known way to reduce the time complexity to solve such an issue, because we can do this in O of n time. And we can sort of leverage the fact that we're, if we can sort of keep track of two things. So if we keep track of what the maximum value is overall, and also the maximum value globally and locally, and then we iterate through, that will help us be able to decide if it's a max subarray or not. So that's sort of where the greedy part comes in. So this algorithm can be categorized as different types of algorithms, but one of them is greedy, and I want to introduce that because we haven't talked about it yet. And a greedy algorithm basically means that you make the best choice in the local moment, which will lead to the best solution overall. So basically, to put that into words, into context of this question, you say you start with -2, and at that stage, -2 is the greatest value. And then -2 plus 1 is -1. That would be the greatest value, so you keep in score of that. But then you get to this part here where you get -3. So then -4 would be, less than the -1. So we keep reference of that -1, and then we sort of move on. And since the elements are contiguous, it actually just works out that, if you go -3, well, that's still less than -1, so ignore that. But then you get to this part here. So basically, as you get to each element, that's going to be the local element. And then you're making a decision to keep the sum of the elements at each local point, which is the best option, which is where the greedy part comes in. And then you're making a comparison to the previously stored global variable. And with all of that, this algorithm is more about understanding the actual intuition as to why we're doing what we're doing, because the solution ends up being quite easy, And it really simplifies what would be a bad time complexity and more complicated code into something quite simple. So basically what we can say here is we want to keep track of both the local maximum and the global maximum. And what we can say here, and we're sort of assuming that we're going to have at least one number in the array, otherwise, it's not possible to calculate the max sum because there's no numbers to calculate the sum on. So what we can say is we can see that the local max is going to be equal to the first number in the array, and that's going to be equal to the global max. So I'm going to set that equal to the local max. And basically we can have a for loop here. And we can actually start our for loop at the element I, missing the first one, because we've already put the first number into the local max. So you just need to think, if you have an array and there's only one number, well, obviously the first number is going to be the maximum number. And it's also going to have the global max as well. And then we're considering the numbers after that, but we have a reference to the previous number, so we can sort of take that into consideration. So we'll let I equal to 1, and we just do this for the length of the array, and then we just increment I there. So what we can say is, well, now we're on the second number, let's say, for the first iteration, and we can say the local max is going to be either the greater of the current number you're on, or the previous local max plus the number you're on. So let's just write that out. The local max is going to be equal, and we can use the math library to get the max of either the number you're on or the local max plus the number you're on. And then basically what you can say is, well, if the local max ever exceeds the global max, we can just go ahead and we can just set the global max equal to the local max. And then after all of that, we can just simply return the global max. So just to sort of go through that again, now we see the code here. Basically, we're looping through each element in the array. So there's an O of n time complexity there. We have these two variables that we're setting. So there's an O of 1 space complexity there. And for each element in the array, we're considering both the local maximum. So basically that could be the number that you're on. But if the number you're on and some of the previous numbers ends up being larger than the current local max, then you need to include that. Otherwise, you just take the number itself. So for example, you could have a negative number, which will make the local max smaller, in which case, the local max plus the nums would be smaller than the value. Sorry, the number would be smaller. Or for example, if you start off with small numbers, the local max would be small, but then you get to a positive number, let's say, then that number would be larger. And you're also keeping track of the global maximum. So if the local max is ever greater than the global max, you can simply set the global max. And then the time you've looped through all of the elements in the array, you're keeping track of the global max. So let's go ahead and submit that code there. And we can see that that beats 97.86%. So that's pretty good.